Hello everyone. I'm going to talk about the finiteness of Selmer groups of zero cycles. So this is joint work with Kalyan Chakravarti, and I'm from SRM University AP, India. So this talk is about something called Chow groups of varieties over an algebraically closed field. So by a field, I mean that it's having some algebraic structures and it has two operations like addition and multiplication, and with these two operations it is forming a group. And I mean, it has k plus is a group and k minus 0 dot is also a group. And there are some compatibilities of these two operations with each other. And x is a smooth projective variety defined over k. It means that x is something by, say, defined by some polynomials, and it is defined by homogeneous polynomials embedded into some projective space. So the Chow group of zero cycles on some variety X, smooth projective variety, is defined as the quotient of the free abelian group, denoted by Z0X, generated by the k points on the variety X. So first you take all linear combinations of these k points, and then what we do is that we take something like a quotient by something called rational equivalence. So an element in the this free abelian group is called a zero cycle, and two zero cycles are rationally equivalent if there exists some curve, maybe reducible, on x cross the projective line, such that if you intersect with the fiber over 0, it will be the zero cycle z1, and if you intersect over the other over infinity the fiber, it will be the other zero cycle. And the quotient of this, as I said, that this free abelian group by this subgroup of rationally equivalent to zero cycles is called the Chow group of zero cycles, denoted by Chow zero of x. Now define a map. It is a natural map from Chow zero of x to the integers. So it is some element of this Chow zero of x will look like summation ni and some points, the classes of some points, and just send it to the sum of the integers, which is the coefficients. The kernel of this map is called is denoted as a0 of x. These are called degree zero cycles. So there is an associated abelian variety corresponding to this x, denoted as Albanese of x. And there is a surjective map from this a0 of x to the Albanese of x. And this is something universal in the sense that if there is any other map from this a0 of x to any other abelian variety, it should factor through this unique homomorphism from this Albanese of x. So this is a very important tool in studying this group a0 of x, this Albanese of x. This is an algebraic variety and it's a smooth projective variety. And it is also having some group operation, so it's a group variety. The prediction of Spencer Bloch and Alexander Berlinson is that the above map a0 of x to Albanese of x is injective. It is surjective, it is known, it's classical, it is known, but it is injective, it's a prediction and a conjecture due to Bloch and Berlinson for x over algebraic closure of a number field. So the question above depends heavily on the algebraicness of this algebraic closure of the number field, and it does not contain a transcendence. I mean, it if it contains transcendence, there are examples. For example, there is the example of Green, Griffiths, and Paranjab, shows that if we consider a variety over the algebraic closure of Q and take one transcendental variable, then we can find some varieties with non-trivial Albanese kernel. That is, there is something in the kernel and the map is not injective. Also, there are other works in the line of non-injectivity of the Albanese kernel by Schoen, Nori, and Guletsky-Gorczynski. So we want to study the group of this a0 of x over function fields of characteristic P from the perspective of something called Wick-Model-Well theorem, which is a very famous theorem for elliptic curves, and try to find explicit description of the Albanese kernel. So we restrict the situation for zero cycles on a smooth projective variety X over the algebraic closure of a function field over a finite field. So the same calculation goes through for number fields, but for over number fields, due to some classical results, the calculations are not that difficult, so I do not present it here. So we consider some abelian variety A, defined over the function field K of C, where K is the algebraic closure of a finite field. In characteristic P and C is a smooth projective curve, and we consider its closure. Consider the map, the addition map, which is like A goes to n times A on the rational points, the algebraic closed field, KC bar rational points of A. The weak model says that if you take the KC rational points of A and if you quotient it by n times this A of KC, this is a finite group. So the proof technique for this weak model well is to define something called a Selmer group associated to A, and to prove that the Selmer group over this function field is finite. So the Selmer group is defined as certain kernel at the level of first group cohomology, where the H1G and the some object which we are considering. For example, here we are considering the abelian variety. So where G is the absolute Galois group of this function field, and I mean the algebraic closure of the function field acting on A. The finiteness of this kernel follows from the finiteness of certain unramified cohomology of the Galois groups at different primes, such that X has good reduction at these primes. So we recall the basic definitions of the Selmer groups. So let G be the absolute Galois group of a function field, and A be a G module, which itself has the structure of an abelian group. That is, there is a continuous G action. So this G is a profinite group, so it's an inverse limit of finite groups. So it's a profinite group, and it has some G action on. I mean, the G is acting on this abelian variety A, and A is also equipped with the topology. G is equipped with the profinite topology. Now consider the continuous map from G to A such that f of sigma tau follows this rule: f of sigma plus sigma acting on f of tau. Such maps forms a group with the addition operation induced from the addition of A. Call this Z1 GA. And then there is a subgroup of this of the form where f of sigma is sigma dot sigma acting on A minus A. So this is a subgroup called P1 GA. And if you take the quotient of Z1 GA by B1 GA, then this is called defined as H1 GA, the first group cohomology of A with respect to the group action of G. So G is the absolute Galois group. Now, the group cohomology is functorial. So in the sense that if we have a group homomorphism from G to H, then you have a map in the reverse direction. That is a homomorphism from H1 HA to H1 GA. And if we have a homomorphism from A to B, then this is covariant in the sense that there is a map from H1 GA to H1 GB. And suppose we have a short exact sequence like given like in this slide. So 0 going to A, going to B, going to C, going to 0. Then we have a long exact sequence at the level of group cohomology. So it takes into account the Galois invariance of each of these Galois modules, and then from CG, which is the Galois invariance of C, the map goes to H1GA and then to H1GB and then to H1GC. Now abelian variety over KC bar, and consider the exact sequence induced by the multiplication by the n map. So A goes to A. A to A, the map is A going to n times A, and the kernel is the n torsions. So this forms an exact sequence over the algebraic closure of this K of C. Then if we consider the long exact sequence in the level of group cohomology, we have this Galois invariance of the intorsions, Galois invariance of A, Galois invariance of A again, and then the connecting homomorphism to H1 GAN. So this Galois invariance of A is nothing but the KC points of A, and therefore the sequence becomes like this in the picture. So I mean the KC points of intorsion points of which are defined over KC, then going to the KC points, then going to again to KC points, and then to H1 GAN to H1 GA to H1 GA. Now V be a prime, and in K of the coordinate ring of C, I mean the coordinate ring of C over K, and if we consider the local field of K of C localized at this V, then take the algebraic closure of this local field, call it KCV bar. Then again, we can call this absolute Galois group as of this local field as GV. Then again, we can do the same thing. So GV to G is an embedding because KC, we have an embedding of KC to KCV, and therefore restriction homomorphism gives a embedding of GV to G. Then we can write down the long exact sequence for this GV and with its action on A. And then we take these two things together. So, like you have a map from H1GA to H1GV and H1GAN to H1GVAN. So then, if we consider the kernel of this given sequence of maps, then we call this as the n-Selmer group of A defined over K of C. From the definition of Selmer groups and by chasing some corresponding exact sequences, you can prove that this A, the Kc points of A quotiented by n times the Kc points of A is embedded into the n-Selmer group of A. Proving the finiteness of the n-Selmer group will prove the finiteness of this with model group, which is the A, the Kc points of A, and then the n times Kc points of A. So our aim is to do the same calculation for some group. This group, what we have defined at the beginning, called A0 of X, that is a smooth projective variety X over Kc bar. So we consider the Galois group G acting on A0 of X, consider the Selmer group in the same way of A0 of X, and we show that this group is finite. The main ingredient in the proof is that the intorsions of A0 of X to A0 of X prime, where X prime is the reduction of X modulo prime in Kc, the coordinate ring of C, is injective. So then reduce the main computation of the above group cohomology for A0 of X, the group cohomology of the Albanese of X, which is a abelian variety, and use the proof technique of the weak model well for Albanese of X, which I have explained earlier just a few minutes ago. And I know that the Selmer group of this n-Selmer group of this Albanese is finite, and some information about the kernel of this map A0 of X to Albanese of X. So this is the theorem. So this the theorem is let A0 of X Kc denote the fixed points of A0 of X under the action of the absolute Galois group. Then the group A0 of X Kc divided by n times A0 of X Kc is finite for any positive integer n greater than or equal to 2. The next is like regarding the finding the Albanese kernel over function field is to prove the model well for A0 of X. That is to prove that something like along the line of model well of abelian varieties, that we can try to prove that A0 of X is finitely generated, which is of course a very big conjecture. It's a dream, but since we have a weak model well, and since there is some notion of heights for zero cycles, so we can try to generalize this for the group A0 of X. So that is something like a big dream, but at least we have some hopes in this direction. So thank you very much for listening to me. Thank you.